Okay, so now we're going to see what a monad actually is. And well, a monad is just two operations and three laws, the monad laws. And what I've discovered in previous years is that the word monad um, often looks scary to students and actually to myself as well. It's like it just blocks the brain somehow. So I'm going to I'm going to try to explain monads and the whole lecture without using that word too often, because it is a kind of abstract, a bit ad hoc concept uh, that emerges when you compare different styles of programming, and then you extract what they have in common. What they have in common, something that doesn't look so intuitive, if you want my opinion, and somebody gave it the name of monad, whatever that word means, right? But it's really just two operations and three laws. So you might think, groups and group theory and mathematics are, I think, three operations and three laws, right? So it's just the same thing, right? You can think of it as a group or as a semi-group or semi-ring, sorry, or whatever. It's not going to be rocket science. So the two operations we've seen before is pure and bind, and a monad is a type constructor M, right? And I think that's where the trouble starts. So it's not a type; it's a type constructor, right? So ring will be, natural numbers are not a ring, but say the reals are a ring. I think at least they're a group. I have no idea. I'm not a mathematician. And yes, so here instead of being based on a type, we're based on a type constructor, a unary type constructor. So a function from type to type. And that makes them higher order, right? Which is already a bit scary, apart from the name monad, which sounds Greek, right? So that's a bad start. But okay, let's. I mean, we've seen option, right? Option is a type constructor. That's not too scary. And then there are two operations, pure and bind, which we've seen before. So pure takes an alpha value and puts it inside the monad. So this is a monad over alpha. It puts it into the box. And bind takes a boxed value, extracts the value, and creates a new monad with it, and that's the one that's returned in the end, presumably. And often alpha and beta will be the same. Like previous example with option not, it was option not all the way down, but in general you can vary the type as you go, which is what we see here. And some people like to compare monads to tacos because that makes them more friendly and especially more tasty. So pure, so you have to think of the type constructor as the taco shell, right? And then the alpha is the contents of the taco, right? The meat, or if you're vegetarian, the non-meat, or vegetables, veggies. So and then everything becomes simpler when you think of monads as tacos, right? Because the pure is simply it takes some meat and it adds a shell around it, right? So it just creates a taco. And then bind takes a taco, removes the meat. I'm just going to say it's a meat, right? The contents, right? Sorry for the vegetarians. So just take the meat out, and then from that meat you create a new taco, and you return that taco somehow. I mean, more or less, right? So different instances of monads might do different things here, but roughly this is the idea, right? And we've seen an instance. We've seen the option type constructor with the pure was option.sum and bind was connect, right? So right, so to summarize here, I think we'll go through this briefly. So pure A just returns a provides a program that has no side effect or no effect at all. It just puts the A in the in the monad without throwing exceptions or anything. That's why it's called pure. Whereas bind will combine MA with F, right? It will first execute MA, and then it will execute F, exploiting the box result of A. So it has access, there's some communication between the two, and communication is done over A, right? So here, let me see, I think I can draw on the screen, annotate. I mean, you can really think of it as being, you know, you have MA is your program. It's not easy to type with that touchpad to draw. And then it's connected to F like this. So first execute MA and then execute F. And the connection between the two is the A value that is, you know, stored inside MA as suggested by the name. Okay. So clear my drawings. There we go. Well, it's the first time I tried drawing. I think it worked. I hope it would. All right. So these are, you know, various type constructors, right? So it's sometimes you just have a type constructor like option, you know, that's a single identifier. But in general, you might have a complex type that depends on alpha, right? I mean, strictly speaking, all of these should have lambda alpha in front, right? So the actual monad here is lambda alpha option of alpha, which by eta is just option, right? But here we've written all of them with alpha in them. We'll see a few. So I mean, most of the lecture will be just going through the most important instances of monads. But we'll, you know, different types of effects, different types of things you can do with you know, with monads. So for example, you can, I mean, we've seen exceptions before, but you can do non-determinism. You can do imperative programming as well, which is quite nice. You can have here the IO monad interacts with the operating system, which is also a form of a side effect. So you have various effects. Some of them are side effects, you know, so you modify some state. Others are, you know, like non-determinism kind of, or exceptions. They're different type of effect. That's what we mean by, you know, programming effects. So it's, you know, these things that pure functional programming doesn't give us, but other cool languages have. And, you know, many of them can be, you know, can be simulated essentially in functional programming by using an idiom, whose name I will not repeat. I mean, monad, of course. Okay. And you can even combine effects. So this is an example here where we have two of them together, but we will not go there in this course. You know, some of them are not executable. It doesn't matter. You know, these programs are not necessarily real programs you can run, but they can still be useful in a proof assistant. And yes, so when you put something in the box, a priori, there's no way to get it out, right? So we've seen that with the signature of pure and bind. So here you have an alpha, and then it puts it in a box. And here you start with a box, and you end up with a box. There's just no way to get rid of the box, it would seem. But each monad can decide whether it wants to have an operation that allows you to get out of the box again, and I think most of them do. Well, maybe not the IO monad. If you write I mean, if you do printf, you write to the console, you know, afterwards you probably cannot tell, okay, this, what have I written, or things like that. It's too late, you've written it. But so for example, with options, you can pattern match on an option, and then if it's a sum, you can retrieve the value, right? So you have a way to open the box if you want. It's just that this is provided outside the monadic framework. This is something the type constructor provides itself, right? So monads is just about the commonality, you know, the very basics, the basic things that they all have in common. And it turns out it's bind, and it's pure, and 3 laws. What are these laws? Well, these laws are just, you know, common sense rules about how you write programs, right? So if you write this program here, you have a pure A and you put it in A prime, and then you execute f of A prime. I mean, at least in my intuitive understanding, this should be the same as you know, just optimizing away the pure step, right? What's the point in putting something in a monad and then accessing it inside the monad when you can, you know, give it directly to the function, right? But this has to be stated explicitly as a law, because otherwise somebody will instantiate the, you know, the monad concept with pure and bind that do not honor that law, and then users will be confused, right? Because what's going on here? You know, these two programs will really do the same, right? And you could say, well, here you have the meat, you put the taco, right? Then you give it to the chef, and then the chef opens the tacos and, you know, takes the meat and gives it to F. You know, obviously I could have given the meat directly to F, right? We'd like these little rules to hold, really, and that's why they are required. So here's another little rule of the same style, which just says, right, so if you inside the monad, you extract, you know, some value A. Here I could have called this one M8, would have been more, maybe more clear. Okay, I will do that for next year, maybe this year even. And maybe I should change it there, otherwise it's not going to be correct. Yes. So if you have a monad and then you extract the A, but of course you extract it only inside the monad, you're not going to be able to run away with it. You only have it here so that you can use it later. But then you return pure of A, right? So you extract the value, apparently you succeeded, and then you wrap it again, right? So that's like, you know, you remove a taco shell and you put back a taco shell. Well, in our little universe, we don't care about, you know, all taco shells are the same. We don't, you know, we don't distinguish them. So, you know, even though some of them are really cool, some of them have, you know, the face of Jesus printed on them and others don't. And you might say, well, these are different, but no. So, or replace your favorite prophet, of course, if you don't like Jesus. Also not a huge fan, to be honest, but yeah, there you go. And here, nested programs, this is when you have some nested computation, like here, right? So you're inside a you're inside a program, and here you're assigning to a variable, but you don't need to do that here, right? You do it inside a for loop, and then you realize, oh, I don't need to do that in a for loop. You can, you know, move it out. So that's what we do. We basically move it out. And then we can remove the, you know, the brackets. They're no longer necessary. So you've seen in this case, we have these curly braces around do. This is supported, right? We can do that. I mean, when you have a block like here, we need something to say where things stop and where things start. But we could also use parentheses around the whole thing, and then we don't need the braces. It's just the braces make it look more like we're actually doing programming in, like, I don't know, Java or C. So we'll use this style. Right, so that's not spectacular. So you see the three monad laws are really not spectacular. They're just saying, yeah, you can move things around if you, and it doesn't matter. And especially in this case, well, it's not really moving things around. It's just moving things out. You know, the computations happen in the same order. It's just that here it's inside the block and here it's outside. Because moving things around could be, you know, problematic. That would be, I think it's a commutative monad, it's called. And not all monads are like this. For example, you might have one line that throws an exception, another line that throws a different exception. And if you reorder them, then you get a different exception. So you don't have equality between the two programs. Here, I've just, you know, moved the first statement of the nested block right before the opening brace. you know, thinking that surely this cannot change anything, and it doesn't because we require it not to. So okay, let's look into our first. Oh no, wait. We're not going to look into anything. We're going to take a little break because this is a bigger section, and then we'll look at something.